Picture this. For countless generations, humanity has gazed upward at the stars and downward into the atom, forever seeking to answer the oldest question: what is the true nature of reality? What are the ultimate rules that govern every flicker of energy, every speck of matter, from the ghostly dance of subatomic particles to the swirling majesty of galaxies stretching across the cosmos? For over a century, the world's brightest minds have been on a quest for a single, all-encompassing answer, a so-called theory of everything that would unify our understanding of the universe. And now, thanks to a revolutionary experiment just published in the scientific journal PRX Quantum, we may be closer than ever before. Are we truly on the brink of a scientific revolution so profound that it would rewrite our understanding of the cosmos? Or are we still wandering, lost in a labyrinth of paradoxes, searching for a glimmer of truth that slips ever further away? To appreciate the magnitude of this moment, let us rewind to the dawn of the 20th century, a time of scientific upheaval and breathtaking discovery. Two monumental revolutions shattered our previous certainties. The first was quantum mechanics, which revealed a world at the smallest scale so bizarre that it defies normal intuition. Here, particles can exist in many places at once, vanish and reappear, and seem to communicate instantaneously across vast distances. The second was Albert Einstein's general theory of relativity, which reimagined gravity not as a force pulling objects together, but as the warping and bending of space and time itself by massive bodies. Both of these theories have been tested, confirmed, and applied so many times that they underpin much of our modern world. Every time you use a smartphone to navigate, or a hospital scans your body with an MRI, you are benefiting from these two pillars of modern physics. But there is a cosmic catch, a rift in the fabric of our understanding. These two theories, as successful as they are fundamentally incompatibles. When scientists try to merge them, the mathematics descends into chaos. Paradoxes swirl, infinities appear, and predictions become meaningless. It is as if nature herself is speaking in two separate languages, each perfectly consistent on its own, but completely unintelligible when forced together. The problem is most acute in the most extreme environments, inside black holes, or at the very first moments after the Big Bang, where both quantum mechanics and general relativity must apply. In these places, our equations break down, leaving us staring into the void of our own ignorance. This is the heart of the mystery. Why can't we bridge the smooth, continuous fabric of Einstein's spacetime with the jittery, unpredictable world of quantum mechanics? The quest to answer this question has given rise to some of the boldest and most creative ideas ever conceived. One of the leading contenders is string theory. According to string theory, every fundamental particle is not a point, but a tiny, vibrating string, billions of times smaller than the smallest atom. The way these strings vibrate determines what kind of particle they appear to be, whether an electron, a photon, or something else. String theory is dazzling in its ambition. It seeks to unify not only quantum mechanics and gravity, but all the forces and particles of nature within a single, elegant mathematical framework. Yet, after decades of development, string theory remains unproven. Its predictions are, so far, beyond the reach of our most advanced experiments. Another imaginative approach is loop quantum gravity, championed by thinkers such as Dr. Carlo Rovelli. Loop quantum gravity proposes that space and time themselves are quantized, made up of microscopic loops woven together at the Planck scale, a realm so small that it is to a proton as a proton is to the solar system. In this picture, space and time become granular, like pixels on a screen, shaking our most basic assumptions about continuity. Lee Smolin, a leading voice at the Perimeter Institute, suggests that the universe is not a collection of separate things, but a single, interconnected whole, where distinctions between objects and events dissolve, replaced by a web of relationships. Despite these brilliant ideas, no single theory has yet triumphed. The search continues, spawning even more radical proposals. Some scientists are exploring whether gravity itself might emerge from quantum information, using concepts like quantum relative entropy. Others are hunting for exotic particles, such as sterile neutrinos, that could help explain the mysterious dark matter that outweighs all visible matter in the universe, yet remains invisible to our telescopes. Theoretical frameworks, such as asymptotic safety and M-theory, an extension of string theory that attempts to unify all its various forms, are being developed and hotly debated. Enter the latest breakthrough, a real-world experiment designed to finally probe the interface between the quantum and the cosmic. In a remarkable collaboration, Dr. Igor Pikovsky at Stevens Institute of Technology, Dr. Jacob Covey at the University of Illinois Urbana-Champaign, and Dr. Johannes Beauregard at Harvard University have crafted a proposal that could, for the first time, let us witness quantum phenomena unfolding in the curved fabric of spacetime described by Einstein. What makes this proposal so exciting is that it is not science fiction. It relies on technology we already possess and could be carried out within the next few years. Let's break down how this experiment works. Picture an array of atomic clocks, the most precise timekeeping devices ever built by humans. These clocks are so accurate that they would lose less than a single second over the entire age of the universe. But these are not ordinary clocks. Thanks to the counterintuitive wonders of quantum entanglement, these clocks can be linked together so that their quantum states are intertwined. Through quantum superposition, each clock can exist in multiple states at the same time, effectively experiencing several different flows of time simultaneously. Now imagine placing these entangled clocks at various heights within Earth's gravitational field. One on a mountain peak, another at sea level, and a third deep underground. Einstein's theory tells us that gravity warps spacetime, causing time to tick at different rates depending on your position. The effect is tiny. Your head ages a minuscule amount faster than your feet because it is farther from Earth's center. But with quantum clocks, even the subtlest difference becomes detectable. By measuring how these entangled clocks tick under the pull of gravity, scientists hope to observe, for the first time, genuine quantum effects in curved spacetime, a real-world test of both quantum mechanics and general relativity side by side. Why does this matter? If this experiment succeeds, it will be the first true verification of quantum theory on curved spacetime, a mysterious regime that until now has existed only in equations and thought experiments. Dr. Pikovsky puts it plainly. The most important challenge remains to combine these two theories into a single one. Something just does not seem to work, and no joint theory has succeeded so far. This is not merely a technical achievement, what could mark the dawn of a new era in physics. The potential consequences are enormous. For one, this experiment could unleash a new generation of quantum technologies. Quantum networks built from entangled atomic clocks could revolutionize the way we synchronize time around the world. Today's GPS systems, which already rely on atomic clocks, could be rendered obsolete by networks so precise that they could enable autonomous vehicles to navigate crowded city streets with centimeter-level accuracy. Imagine fleets of drones delivering emergency supplies, orchestrated to the microsecond, or financial networks executing trades with absolute security and speed. In medicine, ultra-precise timing could help synchronize imaging devices across continents, enabling remote surgeries or new forms of diagnostic equipment capable of detecting disease at its earliest stages. The implications for communication are just as profound. Scientists are racing to build a quantum internet, using entangled particles to transmit information instantly and securely across vast distances. These networks promise levels of security and speed unimaginable with today's technology. In the world of finance, this could mean transactions that are essentially unhackable, protecting trillions of dollars in assets. In science, it could enable distributed computing projects that simulate entire ecosystems, predict earthquakes, or model climate change with unprecedented detail. But the impact goes far beyond technology. If we can finally unite quantum mechanics and general relativity, we may at last answer some of the deepest mysteries of existence. What is the fate of information swallowed by a black hole? What is the true nature of dark energy, the strange force causing the universe to expand ever faster? Could there be extra dimensions of space, curled up so tightly that we have never seen them? And, perhaps most profoundly, what happened in the first moments after the Big Bang, when both quantum mechanics and gravity must have been at play? These are not idle questions. Many of the world's most respected physicists are racing to answer them. Dr. Sean Carroll at the California Institute of Technology argues that quantum mechanics is the most fundamental framework, and that any real theory of everything will be built from quantum principles. Dr. Carlo Rovelli challenges us to rethink our very notions of space and time, suggesting that the universe is not a stage set for events, but a network of relationships, ever-changing, and interconnected. Ginestra Bianconi at Queen Mary University of London proposes that quantum gravity may have an entropic origin, and that mysterious fields could be candidates for dark matter. Kamran Vafa at Harvard University views string theory as the natural extension of quantum field theory, holding the potential to solve these cosmic riddles. Mikko Partanen at Aalto University reminds us that unifying gravity with quantum theory is one of the greatest challenges of modern science, drawing together mathematicians, experimentalists, and philosophers alike. The race is global. Teams around the world are searching for sterile neutrinos, particles so elusive that they may pass through entire planets without leaving a trace. These ghostly particles may be the missing mass that holds galaxies together, the key to understanding dark matter. Others are using entangled photons and gravitational wave detectors to probe the quantum properties of spacetime itself, searching for subtle fingerprints of quantum gravity. Each new experiment brings us closer to the answers we seek, and sometimes to even deeper questions. But as history has shown, every great breakthrough brings risks as well as rewards. The ability to manipulate gravity at the quantum level could usher in technologies beyond our current imagination. Picture propulsion systems that bend space-time itself, enabling interstellar travel not in centuries, but perhaps in years or even months. Some speculate that controlling quantum gravity could unlock new forms of energy, more powerful and cleaner than any fuel known today, transforming industries from manufacturing to transportation. The economic impact could rival or surpass the steam engine, the internal combustion engine, and the internet combined, reshaping societies and creating entirely new sectors. Yet with great power comes enormous responsibility. If only a handful of countries or corporations control the secrets of quantum gravity, we risk deepening the divide between technological leaders and the rest of the world. Ethical questions abound. Who decides how such knowledge is used? How do we guard against unintended consequences, from environmental disasters to threats to privacy and security? Dr. Pekovsky cautions, there is still so much we do not know about how the world works, and many corners of physics remain clouded in mystery. History offers cautionary tales. When scientists first split the atom, few anticipated the dual legacy: nuclear energy and nuclear weapons. The birth of the internet connected billions, but also gave rise to new vulnerabilities, from cybercrime to surveillance. As we stand at the threshold of a potential quantum revolution, we must proceed with curiosity and courage, but also with humility and wisdom. You might be wondering, how does all of this affect your daily life? The answer is, more than you might think. The atomic clocks at the heart of this new experiment are already essential to your everyday routine. Every time you check a map on your phone, track a delivery, or call for a ride, you are relying on a global network of satellites equipped with atomic clocks. Without their precision, GPS would become unreliable, drifting by kilometers each day and rendering countless modern conveniences useless. The next generation of quantum clocks could make these systems even more accurate, opening the door to smart cities, autonomous vehicles that never get lost, and seamless global logistics. Quantum technology is not just for scientists in white lab coats. Banks are investing heavily in quantum encryption, seeking to keep your financial data secure from hackers. Hospitals are piloting new quantum sensors that can detect disease earlier than ever before. Farmers are experimenting with quantum-enhanced weather forecasts to protect their crops from storms and droughts. In short, the deeper we probe the universe, the more we discover tools that solve real-world problems, often in ways no one could have predicted. Looking forward, the successful union of quantum mechanics and general relativity could transform how we view our own existence. If time is not a continuous river but a quantum tapestry, could we one day learn to manipulate its flow? Might we develop technology that slows aging or creates virtual realities indistinguishable from life? Some visionaries speculate that a quantum theory of gravity could unveil new forms of consciousness or even new definitions of intelligence, forever altering what it means to be human. These ideas may sound like science fiction, but history tells us that today's wildest theories often become tomorrow's everyday tools. When James Clerk Maxwell wrote down the equations of electromagnetism in the 19th century, no one imagined that they would lead to radio, television, or the wireless internet. The quantum discoveries of the early 20th century paved the way for lasers, semiconductors, and the digital revolution. It is entirely possible that experiments with entangled atomic clocks today are planting the seeds for a quantum leap tomorrow. So, will this new experiment finally unite our understanding of reality? We are closer than ever before. But the ultimate answer remains just out of reach. Every discovery, every failed experiment, every new idea brings us a step nearer to the ultimate goal. A single, elegant set of rules describing reality itself. As Dr. Carlo Rovelli so poetically puts it, we are not just learning about the universe, we are learning about the very fabric of existence. If you want to stay ahead of these world-changing discoveries and understand how they might shape your future, make sure you subscribe and join the conversation below. If you could bend gravity or harness the quantum internet, what would you create? Would you design new sources of clean energy, build cities that float above the ground, or find ways to communicate across the stars? Or do you worry about the risks, about who holds these powers, and how they are used? Share your thoughts in the comments, and let us explore the future together. Because the greatest adventure is not just out there among the stars, it is right here, in our